Hello there. This is Doug Rumbaugh. Lately, I've been playing around with benchmarking some things, and in order to speed up the amount of time that it takes to complete these benchmarks, I started playing around with multi-threading, and I found something interesting. In hindsight, it's really not that interesting, but it took me a split second to figure out what the hell was going on, so I think it might be worth showing it. So what we have here in front of us are the results of this benchmark program I've been playing with. I am measuring two things. I am measuring latency and I am measuring throughput. So latency is the amount of time that it takes from when I call the function that I'm benchmarking to when I get my result. And throughput is the number of times that I call the function in a given per unit time. So latency here is measured in seconds and throughput is measured in function calls per second, completed function calls per second. And all that I'm doing to measure this is I have a loop that calls the function a bajillion times, and then I measure the amount of time that it takes to get the latency figure, and I measure the total amount of time for the whole outer loop to get the throughput figure. Now, in order to improve the precision of my latency numbers, what I'm doing is I'm actually, in fact, let me just show you the code. What I'm doing here is here we go. Excuse this code's a mess. I've just been playing around with it. Um, what I'm doing here is this is my big outer loop, so I'm calling this thing n times. And then to actually get the latency of the function, because these functions return really fast, what I'm doing here is I'm actually calling the function inside of a loop m times, and then sort of calculating the average per call time, and using that to accumulate my latency figure. Right, so I'm calling this like a million times, and then dividing the total time it takes by a million in order to get my latency. So this is an embarrassingly parallel operation. There's nothing in here that depends upon any other iteration of this loop. They're all completely independent. So I decided to try parallelizing it to make things go faster. So what this is going to do is it's going to spin up a bunch of independent threads. Each thread is going to run certain iterations of this big for loop. So I'm not parallelizing this because that would mess up my latency measurement, but I am parallelizing the big outer loop. And my goal was just to make it so I didn't have to sit around for quite as long to get my answers. And in doing this, I discovered something kind of interesting, which is perhaps actually not interesting because it makes perfect logical sense. But I found it interesting, and it took me a second to figure out what the hell was going on, so I thought that I would record a quick video to show you what it is that I found. Now above here, you can see the results of running this program. This is the hash test program. One of these was compiled with multi-threading enabled, and one of them was compiled with no multi-threading. Now I have actually blurred out the throughput numbers because what I'm mostly interested in right now is the latency numbers. And you'll notice that surprisingly, the latency is actually different. Not much different, about a factor of 2, but it is different. Now take a split second, see if you can figure out which one of these was compiled with multi-threading and which one was compiled without. Okay, now I'm going to reveal to you the throughput numbers. Same question. Can you tell which one of these was compiled with and which one was compiled without multi-threading? So let's take a look at these numbers because something interesting is happening here. The answer is that this first one was compiled with multi-threading and this second one was compiled without multi-threading. And what you should notice looking at them is that the latency goes up when you introduce multi-threading in this situation, right? So my latency went from 3 to 6 nanoseconds. But my throughput went up by an order of magnitude as well. So the latency goes up and the throughput goes up. And this seems somewhat counterintuitive because one would think that the latency and the throughput are proportional to one another. And in fact, that is the case whenever you're doing things serially. So if you run 1,000 operations, each operation takes 250 milliseconds, right? If you decrease the amount of time, if that 250 goes to 200, then the throughput's going to go up because it takes less time to do each one. That makes intuitive sense. But as soon as multi-threading enters the mix, that whole thing goes out the window. And what you see here is that, at least with the default number of threads here for OpenMP, the latency doubles, but the throughput goes up by an order of magnitude. So they're both increasing. Seems a bit odd. So I decided to investigate a little bit further. And what I did is I set up a simple little script, and I apologize in advance, this is a really ugly script. But I set up a quick little script here to create a CSV file showing the number of threads versus the number of threads, the throughput, and the latency, just to get a look at what those numbers look like at scale. And I went from 1 thread to 100 threads. And the results are kind of interesting here. So let me do this. Okay. So here are the results for 0 to 100 threads. Let me punch in here a little bit. This first graph shows the throughput in hashes per second. I'm measuring hash functions. So hashes per second versus thread count. And as you can see, what we get is we get this effectively linear scaling for a short period of time, and then it flatlines. Meanwhile, if we look at the latency graph, it's flat, and then we get linear scaling. And remember, these two quantities, throughput and latency, are kind of inverse of one another. So we want high throughput. Throughput high is good, and we want latency to be low. And just to get a slightly better idea of what's going on here, I graphed just the first 16 threads. So if we scroll on over here, we can see the same graphs, but only with the first 15 or 16 threads. And what we see here is on throughput, we get this nice straight line up to 5 threads. And then it drops a little bit at 6, but that's probably just noise. I only took one data point for each one of these because this data takes quite a while to collect. So I only have one data point there. That's probably an outlier, just some noise. But we get 5 and then 6, and then it's flat. So we get linear up to 5 and then flat line across after that. And likewise, for our latency measurements, we're flat up to 5, and then we start linearly increasing past that. So what's going on here? Well, can you guess how many cores my CPU has? So I'm running an 8700K, which is a 6-core CPU. I get a beautiful linear scaling at no extra latency for the first 5 threads. That makes sense because I have a 6-core CPU, right? It can easily handle doing those 5 things at a time at no extra cost. But the moment I start increasing that, then we have to start swapping processes in, or swapping threads rather, in and out. And so we're going to see not really much of a gain here for throughput because I'm still only able to do 5 things in parallel. I mean, technically I can do 6 things in parallel, but I got to run the operating system too, right? So I'm really only doing 5 things in parallel. And so the amount of time that it takes between function returns is going to go up because those functions aren't running to completion. It runs it halfway and then swaps to another one and runs that one halfway and then swaps back and finishes it. So I'm getting into all my operating system's concurrency controls that are slowing things down. And meanwhile, because I'm not doing more stuff in parallel, it's completely flatlined here. Now, of course, we would probably see additional scaling of the throughput were my workload bottlenecked by something other than the CPU, right? This is just calculating hashes. It's happening entirely in the CPU. But if there were, say, disk I/O or something involved, then we might see further scaling of the throughput even past 5 threads on this particular computer because it can process other threads whilst threads are waiting for the disk I/O, right? So we'd potentially see more throughput through there. I'll, of course, experiment with that as well. But that's sort of what you get. Now, the other thing to bear in mind is we get this beautiful linear scaling for throughput and this beautiful flat line for latency up to effectively my number of cores for this workload that is completely CPU bound, and B, embarrassingly parallel. I don't have to do any concurrency controls on this thing to make it work. What you would see in practice for real workloads, and that's where I'm going next with this benchmark. That's why I'm even doing this, is I want to benchmark hash tables. What you end up with real workloads is that you have to integrate a bunch of concurrency control into this thing so that your different threads aren't stomping on each other, right? If you're operating on shared data or something, you have to make sure that two threads aren't writing to the same thing at the same time and things like that. And that's going to bog stuff down quite a bit. As a matter of fact, I found this rather interesting. There's this paper staring into the abyss. It's quite old, but it's worth a read if you're interested in this sort of stuff. I'll go ahead and open this guy up. It is written by these people, and it was a VLDB paper a number of years ago, 2014. And so what they did in this paper is they simulated, using a server cluster and some software, a 1,000 core CPU, and they set up a database on this 1,000 core CPU, and they ran a bunch of benchmarks. And so one of the benchmarks they did is this YCSB workload, which is a write-intensive workload, so writing lots of data to this thing. There's lots of writes in the mix that allows you to adjust the skew of the workload, which effectively means this. Theta here is the skew. So when theta is equal to 0, what that means is that the records that are selected to process or operate on are pulled from a uniform probability distribution. So effectively your writes are spread evenly throughout all of the data. And then as you increase the skew, you start to focus most of your work on an increasingly small section of the data. Now, what this means in practice is that when your skew is low, so say theta is equal to 0, your writes are spread out across the data set such that your concurrency controls are not going to force your threads to wait very often, right? Because if I'm writing to some data up here simultaneously with writing some data down here, those two threads are independent of one another. So the thread down here is not going to have to wait for the one up here, most likely. It depends on the specific nature of the write, but frequently that's the case. Whereas if all of my writes are focused on a relatively small chunk, they're going to spend a lot of time waiting for each other. And so what we see here then is that when the writes are uniformly distributed, spread out across all the data evenly, we get a nice linear scaling up with the number of cores. Because they're not in contention for the same records in the database, they can pretty much do what they want in parallel with one another and not get held up. However, we see with the gray line here, the 0.6 theta, that we do reach a point where it flatlines as we scale the number of cores when there's a bit of skew in the writes, because the writes start having to wait for one another. And then when there's a lot of skew, say theta is equal to 0.8, what we see is that it doesn't even really get a chance to flatline, at least not with the data that they collected here. We instead get this arc where it goes up and then it goes down to the point where running with a large number of cores or a large number of concurrent transactions that are running in parallel, we do worse than we did with a fewer number of concurrent transactions running in parallel. And that's because you have a bunch of transactions that have to sit and wait, which reduces your overall throughput, especially when you have to account for deadlocks. And so what I mean by deadlocks is what can happen is if two transactions require locks on intersecting records in the database or intersecting sections of the database, they can get the locks in such a way that they block each other from finishing. So let's say we have three chunks of data of interest, A, B, and C, and we have two transactions. Transaction 1 is going to lock A, C, and B. Transaction 2 is going to lock B and C. Well, what can happen is transaction 1 comes in, locks A and C, and transaction 2 comes in and locks B. Now at this point we have a problem because transaction 2 is going to wait until transaction 1 releases C, and transaction 1 is going to be waiting on transaction 2 to release B. So we have a deadlock. Neither transaction can go anywhere. And so what winds up happening is the database has to A, figure out that there's a deadlock, and then B, kill one of those competing transactions. And that can cause, as you'd imagine, some issues with throughput when you're killing transactions or when transactions are waiting. So those are all things that come into play and result in this tapering off of throughput when you have lots of transactions trying to access the same set of data. So you have issues with concurrency control slowing things down. So this whole concurrency thing is a little bit more complicated than one might at first think. More threads is not necessarily more better. It all depends upon the specifics. So I'm going to keep pursuing this and playing around with hash tables specifically. One thing I want to do, and you'll have to let me know in the comments if you're interested in this, is I only have 6 cores on this particular computer. However, upstairs, there's a computer because a certain person whom I live with is obsessed with having the best of everything. There's a computer with a Threadripper 3990X 64 core processor. So I'm going to, I think, run this same set of benchmarks and whatnot up on that computer and see what the graphs look like when there are 64 cores. See if we still get that nice linear scaling up to here on the graph. That would be pretty nice. If you're interested, let me know in the comments and I can record a video about the results from that as well. In any case, I hope that you found this interesting, and I'll see you in the next video.